Hi, I'm doing exercise 4.28, and I'll get into it. All right, so this problem, if I did it right, takes two inductions. So I'll get into the first one. So the first one is we're going to try and show this. Um, so for every term, I think one thing quickly is I'm pretty sure that this n is actually supposed to be a capital N. So if that's, I believe that's right. But all right, so the first step is the base case. So all right, so we know that a is positive and less than or equal to 1, so the base case, I guess we could just do both. So if a is 0, or like a0 equals 0, 2 to the 0 is 1. So a to the 0 checks out, and then if the first term is 1, 2 to the first power is 2, so that also checks out, so the base case works. Now for the inductive step. All right, so for the inductive step, we assume that that any term of the series. So we assume that an, assume an. We assume this term is less than or equal to 2 to the n. And I'll switch both these to uppercase actually, just to stay consistent. All right. We want to show that given this, we want to show that a to the n plus 1 is less than 2 to the n plus 1. All right, so let's see. All right, by this stipulation right here, we can say that basically a to the n plus 1 is less than or equal to the sum of all the terms up to an, or up to n. So a0 plus a1 plus everything up to an. All right. So by this stipulation right here, we know this is true. Okay, what else can we do from here? We're trying to show this. Well, we can say that this series right here is less than the series 2 to the 0 plus 2 to the 1, all the way up to 2 to the n. Let me fix this n again to be consistent. All right. So how do we know that? Well, basically, again, this step right here basically says that each successive term in the series is less than the sum of all the terms before it. We know that the series either starts with 1 or 0. So let's say, let's say a0 equals 0. That means a1 would have to be also equal to 0. But we know that this is equal to 2. This term right here is equal to 2. And that pattern continues. If a0 is 1, then this term also has to equal 1. But if this is 1 right here, and then this is 2. So if you add these, you get 2. If you add these, you get 3. And this pattern, it's pretty obvious to see that this continues. So this side basically is always bigger than this side. All right, what can we do from here? So we want to show that this guy right here is less than or equal to this guy right here. So let's see if we can do that. I'm just going to actually say that we can and then prove it. So yeah, okay. So 2 plus 1. All right. So I just kind of stipulated this, but if we can show that this is true, that like this inequality right here is true, then we'll have solved the problem because we'll have shown that this inequality is true. All right, but we haven't done that yet, so we still have to show this. So let's see how we can do that. Okay, well, one way to start is by saying that 2 to the n plus 1 is just equal to 2 to the n plus 2 to the n. How do we know this? If we factor out 2 to the n from each of these terms, we just get 2 to the n times 1 plus 1, which equals 2 to the n times 2, which just equals 2 to the n plus 1. All right. So I've stipulated this right here. So I'm gonna get rid of this term, so it's easier to see. So we have a 2 to the n on both sides of this inequality. I'll move this over so it's a little clearer to see. We have 2 to the n on both sides of this equality. So taking 1 out of each side will not do anything. So I guess we could first cross that out. We cross this out and cross this out. So now we have 2 to the 0 plus 2 to the 1, all the way up to 2 to the n minus 1 is less than or equal to 2 to the n. For our purposes, I'm just going to like raise each of these. It's just, I mean, I'm just going to index this, each side of this. I'm just going to say, instead of 2 to the n minus 1, I'm going to say 2 to the n, and then 2 to the n plus 1. All right. So now this is kind of part 2 of the problem. We want to show that this relationship holds. All right, so I'll kind of start fresh. So part 2. All right. We can write this in summation notation. So we want to show that to the so all right, so we want to show this. All right, we'll get into that now. Okay, so so for this we're gonna need another base case. So base case. This is the second induction. So base case. Let's say n equals 0. So we'll have 2 to the 0 is just 1, and that is less than or equal to 2 to the 0 plus 1 equals 2. So yes, 1 is less than 2. So the base case checks out. Now for the inductive step. All right. Okay, I'm gonna write this guy again like in an expanded form. So we have 2 to the 0 plus 2 to the 1, all the way up to 2 to the n, and we're supposing that this is for the inductive hypothesis. We suppose that this is less than 2 to the n plus 1. All right, so that's our inductive hypothesis. So we assume this is true, and we want to show that basically we want to show plus 2 to. All right, that's what we want to show. Okay, so the important step is for us to notice something about this term right here. So notice 2 to the n plus 2, or else notice 2 to the n plus 1 plus 2 to the n plus 1. So 2 to the n plus 1 plus 2 to the n plus 1 is equal to 2 to the n plus 2. Again, a quick way to verify this is to factor out each of these terms. 2 to the n plus 1. And we can see that by the rules of exponents, this is just equal to 2 n plus 2. All right. So I'll rewrite what we want to show given with this instead of this. So we want to show that all of this is less than or equal to 2 to the n plus 1 plus 2 to the n plus 1. So right. Well, we supposed in our induction hypothesis, I'll copy it down here. We supposed to this. Now we can see that what we want to show, we'll get what we want to show. Oh, shoot, I don't know what that was. We'll get what we want to show if we just add 2 to the n plus 1 to each side, which preserves the inequality. So plus 2 to the n plus 1, 2 to the n plus 1. Yeah, so this is exactly what we want to show. These two are equal and these two are equal. And adding something to each, adding the same thing to each other, the inequality preserves the inequality. We know again that this is just 2 to the n plus 2. Yeah, so we did everything we wanted. We showed that this first induction was correct by doing induction on this last step of the inequality right here. So right in red, we've shown that a to the n plus 1 is less than or equal to 2 to the n plus 1. And yeah, that's it.